We were working in section 4.4, the Fundamental Theorem of Calculus last time, and I believe we're on example 5. Remind you a couple things of what we had done. The Fundamental Theorem of Calculus says that if you have the definite integral from a to b of f of x dx, that is the same as the antiderivative evaluated at b minus the antiderivative evaluated at a. And then we had a second fundamental theorem of calculus that said that if you take, basically, if you take the derivative of the antiderivative, you end up getting back the original problem. And Evan had asked me a question last time about this one, which I thought was a really easy one to show you how this works. So let's actually take a look at what this does if you actually take the antiderivative and then you take the derivative afterwards, so you can see why the fundamental theorem of calculus, when you have like not an x up on top, you've got another function, why you end up having the chain rule involved. So what I'd like for us to do is to do the same problem again, but we're going to actually do all the pieces of it that we kind of get to avoid doing with the fundamental theorem. But let me show you how it, or why it works. So if I were to take the antiderivative of t plus 2, what would I get? T squared over 2 plus 2t. And then I would evaluate it at sine of x and at 0. Now if I evaluate this at sine x, I'm going to get sine of x squared. I'll put the 1/2 in front. You could write it over 2 if you want, but it's 1/2. And then 2 sine of x here, right? And if I evaluate it at 0, I get 0 and 0. So none of that actually ends up mattering. Anytime I evaluate a constant, things do tend to fall apart. Especially, well, not all the time, but on this one when I've got the 0, they do. What does happen is no matter what happened at the value at the end there, once I take the derivative here in a moment, it will go to 0. So if I want to take the derivative of this now, so let's now actually go back up and finish out that the whole point is that we're going to go back in here now and we're going to take the derivative, right? So our goal is to find the derivative of this thing. So I want the derivative of 1/2 sine of x quantity squared. So that kind of looks like some of the things you guys were doing on your derivative gateways back in the day. The 1/2 stays. The 2 will come down. I rewrite the sine of x to the value 1 less than 2, which would be 1. And then I have to take the derivative of sine, which is, of course, cosine of x. And then I've got the derivative of 2 sine x, which is 2 cosine of x. And what I want you to notice is that this simplifies to being 1. I end up with cosine in both terms. So I'm going to factor the cosine out. That leaves me with sine of x plus 2, which is the same thing as this with the sine plugged in times the derivative of sine, which is cosine. Okay, so there's the chain rule actually showing up in the process. And there's no expectation for you to do that on any of the problems, but that's what you're shortcutting by having the Fundamental Theorem of Calculus Part 2. Okay? All right, let's go ahead and move on then to example 5, which is where we were last time. We're asked to find the given area, and it's the area of the region bounded by the graphs y equals x squared, x equals 2, and the x-axis. So we need to draw a picture, and I do hope that some of you have your calculators handy so that you can tell us what this looks like. Y equal x squared is a parabola. So we've got this shape roughly like so, right? The x-axis, that's down here on bottom, so I'm going to mark that in red. So we have the x-axis down here, and it says the line x equal 2. What does the line x equal 2 look like? Good, it's vertical, right? Over here at 2. So it looks like this. So I'm supposed to be trapping I'm supposed to be shading the trapped area by these 3 curves, and as you can imagine, this is what it's referring to right here. I've kind of shaded not inside of my lines, but you have the idea, right? So what we're doing now is we're taking this particular picture to find the area that it's referring to. There's no problem actually set up and given to us in this until we've created the image and can actually figure out what our definite integral is that we're trying to find. So this is the definite integral of this function x squared dx. But what I'm trying to find in drawing this picture is the upper and lower limits of integration. So somebody tell me one of the limits of integration. 0. So I started my blue shading at the y-axis, or the origin actually, right? What is the upper limit of integration then? It's 2. All right, what's the antiderivative of x squared? X cubed over 3. And we're going to evaluate that at 2 and at 0. So evaluating at 2 means I have 2 cubed over 3. Evaluating at 0 means I have 0 cubed over 3. This is one that's probably clean enough that putting it in your calculator and doing function integration would just be a waste of time, right? What is 2 cubed over 3? 8/3. All right, any questions on that one? All right, the last thing in this section is the average value for integrals. So it says if f is integrable on the interval from a to b, then the average value of f on a to b is to take the definite integral from a to b of f of x dx and then to multiply it by 1 over b minus a. So what we're going to do on the next problem is we're going to do this process, but I'm going to show you in a calculator what it's actually doing when you find the average value, what you're physically doing to a graph. Okay? So the only difference between this and what we've done before is this extra constant factor at the front, 1 over b minus a. That's it. So here's our function. And of course, as you remember, it's more helpful to think about this as x to the 1/2 for our purposes. It wants us to find the average value. So the average value is 1 over b minus a. Well, b and a are this 9 and 4. My integral is from 4 to 9 of x to the 1/2 dx. All right, so 1 over 9 minus 4, what is that? 1/5, right? What is the antiderivative of x to the 1/2? Right, so we've got x to the 3/2, and then dividing by 3/2 is the same as multiplying by 2/3. And we're going to evaluate this from 4 up to 9. And if you'd like, it might even be more helpful to rewrite it back in radical notation. So this is the square root of x cubed evaluated from 9 to 4. You don't have to do that, but it is often easier to think about it that way, I think. Because the 1/2 and the 2/3, I can go ahead and simplify those to 2/15, I believe. And then we need to evaluate these. So what happens when I plug in 9? What is the square root of 9? 3. And 3 cubed would be 27. So that's plugging in the number 9. So that gives me 27. Now let's plug in the number 4 together. I need to do 4 square rooted. I want to square root first when I can. It's easier. The values stay smaller. What's the square root of 4? 2. And then 2 cubed would be 8. Okay, so this is minus 8. What is 27 minus 8? 19. And then 19 times 2 would be 38 over 15. Okay, so what I want to show you, though, is I want to show you what you actually found. I mean, like, we can do some little bit of, calculus and algebra and find this thing, but what in the world did we actually find? Take your calculator, if you have it with you, and I want you to put in the original equation, so the square root of x into y1. Okay, put in square root of x. And then I want you to manipulate your y or your x window for, I want you to manipulate your window for your x values. So hit window, and I want your minimum to be 4 and your maximum to be 9, right? Because I'm supposed to be going between 4 and 9. I want to be a little bit careful because I want to see down to the y-axis, down to the x-axis, excuse me. So let's make your y values minimum be 0. And then the square root of the value 9 is 3. So where y minimum is max will be 3. So I've said all of that. Let me write that. So my x min is 4. The x max is 9. Your y min is 0. And your y max should be 3. And you should have an image. You're not going to see the y-axis because I told you to start it where I told you to start it, but your whole image looks like this, and your window should look something like between here. Do you have something that looks roughly like that? Okay, great. Hit y equals again, and in y2, I want you to put 38 over 15. Okay, just y2 is 38 over 15. What you should see in your calculator now is a horizontal line. That's not horizontal. Let me just draw it freehand. Cutting through your graph roughly like that. Do you see that in your graph? So what is your graph actually doing when you find average value? Well, imagine that your graph is Play-Doh, really thin Play-Doh. Okay, so it's flat Play-Doh. What you've done is you've chopped off this little corner of the Play-Doh and you've reworked it and it fits right here in this corner. You've averaged out this irregular, odd-looking height to turn it into a rectangle. The rectangle has height, in this case 38 over 15, and it has width, in this case 5, because we went from 4 to 9. That's what average value does. Is average value changes your shape into a rectangle. It gives you the height that you would actually have to have on average for the width that you were given already. Does that make sense? The reason I point it out is because that means that if you get an answer and you put in your calculator as y2 and the other one is y1, and you put the appropriate parameters in there for the x values, and you're not seeing something cutting through that seems to be balancing out these heights, you know you've got a wrong answer. You know you've made a mistake somewhere, and you can go back and take a look at why. Any questions on average value? Okay.